Welcome to this week's lecture. In this lecture, we'll be continuing our discussion of biostatistics in the vein of comparing different results between two or more groups. By the end of this presentation, you should be able to select the appropriate statistical test to perform a given research question. You should be able to correctly interpret the results of comparative analyses in the context of a clinical study, and you should be able to differentiate between logistic and linear regression analyses and talk about when regression analyses are needed in the literature. Let's start out with our clinical dilemma. Let's say that you've just completed your first randomized controlled trial, but unfortunately you didn't specify which statistical tests you perform in your methods section, so shame on you. But your local IRB did not catch this oversight, so shame on them. Your study involves a comparison of mortality rates, which is a nominal variable, between two groups, lisinopril and placebo, in patients with congestive heart failure. Following your data collection, you find that the incidence of death in the lisinopril group is 3%, whereas the incidence in the placebo group is 4%. So you're aware that the relative risk is 0.75, but you need to perform a statistical test to know if that's statistically significant and not due to chance alone. In order for this to happen, you need to know which statistical test to perform to obtain your p-value. The question is, which test should you use in this circumstance? The first part of this lecture will focus on the statistics involved in comparing results in multiple groups. The intent of this video is not to ensure that you have an intense mathematical understanding of the various tests. It's just to ensure that you're able to read an article, interpret the test results, and ensure that the investigators perform the correct test given the variables and number of groups involved. Let's put our statistical testing into some context. So we're running statistical tests, remember, under the umbrella of statistical significance testing. So we're trying to quantify the probability of obtaining our observed results, or more extreme results, assuming that no difference exists at baseline between the groups in the larger population from which the sample was obtained. So we're performing an analysis on a random sample from a representative population so that we can use our results to infer certain conclusions about that population. When we would perform a test between two groups, we state the study hypothesis, so the alternative hypothesis, and then we state the null hypothesis, which is the hypothesis of no difference. We decide a significance value, the alpha value, and we also talked about last week how we also decide on a beta value and an appropriate sample size given our clinical question. We then run the experiment, collect the data, and then we use an appropriate statistical significance test to obtain a given p-value. Using the p-value, we then come to our ultimate conclusion to reject or fail to reject the null hypothesis. So we're really looking in depth today at step 5. This lecture is not to be an all-encompassing look at biostatistics. There are a lot of different statistical tests that are used in the medical literature. We're going to focus on some very common types, and a flowchart will be provided to you at the end of this video and also on your quiz. So you don't have to remember or memorize the flowchart, but you just need to be able to use it and ensure that investigators are running the appropriate statistics. So selecting an appropriate statistical test depends on a number of factors, and we're going to focus on 3. The first one is whether the outcomes that are used or the variables in the study are from the same individuals or dependent on one another or from different individuals, in which case the variables and outcomes would be considered independent. They're not dependent on other variables and they're not from the same patient. The second factor is the number of groups that are being compared, typically 2, but sometimes 3 or more. And the third factor is the type of variable that's being analyzed in the study. Is that variable nominal, is it ordinal, or is it one of the continuous variables, interval, or ratio? The type of variable also has another caveat. What test we use also depends on the distribution of the variable. Is it parametric or normally distributed, or is it non-parametric and non-normally distributed? We'll go into each of these factors in a little bit more detail. Again, to put statistical testing into a broader context, we're using these tests to analyze differences in the outcomes between two or more groups to determine whether a significant difference exists between them. So we're essentially asking if we have a study of two different groups, whether those groups are from the same population, which is what is predicted under the null hypothesis, or if they're from different populations, they're significantly different, in which case we would reject the null hypothesis. We're really assessing the compatibility of the results with the null hypothesis of the study. And again, the value we use to characterize this is the p-value. An example would be the null hypothesis of our dilemma at the beginning was mortality in the lisinopril group divided by the mortality in the placebo group is 1.0. The null hypothesis says there's no difference, but we want to prove that there is a difference potentially within a given range of randomness, and that our alpha value is 0.05, so we're accepting a 5% chance that our results will be due to chance alone. When we run the statistical test, we'll generate what's called a test statistic, which is simply the result of the statistical test. Each test has an associated distribution and table with which you can compare the test statistic to determine the associated p-value. Then you compare that p-value with your alpha value, which you established before the test was undertaken to assess significance. So specific test statistics will vary by test. For example, there are things called t-scores, which are generated from t-tests. F-scores are generated from ANOVAs. But no matter what the score, they all correspond to a given p-value, which we then compare for statistical significance. When we're performing a statistical test, we're trying to get all the results of our study down to a single number. What the tests are doing in essence is assessing the distribution of the test statistic when the null hypothesis is true. Again, this test statistic will vary based on the test, but for categorical data, the null hypothesis is going to be a relative risk of 1.0. So we're essentially getting all of our results down to a single estimate or result, which is risk, which is then generated into a specific test statistic based on whatever test we use. When we create the distribution of the test statistic, the center of the distribution will be the mean under the null hypothesis. So if we look at the study at the right, the true value under the null hypothesis, if it's categorical, the null hypothesis says the relative risk is 1.0. So 1.0 would be the center. Then we compare the two groups. If the relative risk is far away from the mean of 1.0, for instance, if it's 3.0, which is several standard deviations away, then it's very unlikely observation to generate, assuming that the null hypothesis is true. So it'll be associated with a small p-value. Then we'll probably reject that null hypothesis. For continuous data, our null hypothesis is centered around 0 because the incidence of group 1 minus the incidence of group 2 is not 1, but it's 0, which means that when we create the distribution that our statistical test is using, the mean value of 0. But if we have some sort of data point like 3.0, say the difference between means is 3 instead of 0, that might be very unlikely depending on the standard deviation of mean and other things. So again, we would likely generate a small p-value leading to rejection of the null hypothesis. So this is confusing. Let's take an example of a test statistic calculation. An investigator wants to determine if her new blood pressure medication works better than placebo. So she has a two-group study which uses different patients in each group. So she has independent groups. She has two groups, the medication group and the placebo group, and she's assessing blood pressure, which is a continuous variable because it's a ratio variable. Let's say, for argument's sake, that this variable is normally distributed. In this case, we would use what's called a two-sample t-test, or just a t-test. The equation for it is listed at the right. Please do not memorize this equation, but let's just walk through what the calculation means. So in the numerator, it's saying that mean 1 is being subtracted from mean 2. So if your blood pressure was 140/90 for mean 1 and 130/88 for mean 2, then the mean difference is about 10 millimeters of mercury. Then you're dividing that by the standard deviation of each group and by the square root of the sample of each group. So our ultimate test statistic is about the difference in the group means, but it also incorporates aspects of the standard deviation and sample size of the groups. So the null hypothesis would be that there's no difference between groups. So for the t distribution in this case, it would be centered around a mean difference of 0. Since in this case I made up a test statistic or a t-statistic of negative 3.78, that's far, far away from the mean of 0. It's over 3 standard deviations away, so if I compare that test statistic to a t-distribution table, it would tell me the p-value, and the p-value in this case is less than 0.01. So I would expect this result due to random chance, assuming the null hypothesis is true, only 1% or less of the time. So in this case, I would reject the null hypothesis. Again, not important to memorize anything, just looking at how test statistic calculations are performed. Let's now get into how to choose an appropriate statistical test for your particular study. The first question that we'll be looking at is determining whether study variables are independent or dependent. For data in a study to be called independent, observations between the groups and observations within groups should both be disconnected from all other observations. So that's what independence means. Dependence would mean that the observations between groups or within groups are in some way connected and therefore affect one another, and that can bias your study. So what we're going to focus on is independence between groups. So if, say, you're doing a test, which is a pre-post study on a single group of patients, so an example of this would be if I made up a test in which I test your drug literature knowledge before the semester began, and then I give you a test at the end of the semester, and I look to see the difference between those two data points. Your data points in this case are dependent on one another. They're drawn from the same individual participant, so that your follow-up data points, which is one of your group results, depends on your baseline data points, which is your other group of results. That's what is meant by a dependent study. The variables in that case are dependent. If you want an independent study, you need to use 2 or more distinct groups of patients to make sure that the observations are not related in any way. There's also something called a between observations independence or dependence. We're not going to assess this, so don't worry about this, but in general they're less common, but some variables in a single group may be related to or impacted by other variables. This sometimes happens when observations are too close together in time. It could also be a result of sampling error, but for our purposes, think of independence and dependence based on whether the variables come from a single group of patients or multiple groups of patients. The second question we need to ask ourselves in determining which statistical test is most appropriate is how many groups are involved. In the biomedical literature, most studies involve a comparison of 2 groups. You can think of a placebo-controlled trial. 2-group tests are really assessing the probability that the results stem from 2 different populations. So we have one group and then we have another group, and the statistical test is essentially going to treat them as different populations if in fact they are statistically significantly different from one another. So you have your single group and then you compare it to a different group, essentially saying, are my results compatible? So a bivariate or 2-group analysis is really telling us whether the 2 groups are significantly different from one another on our outcome of interest. However, there are tests which assess differences between 3 or more groups. The most common example that you'll run into is the ANOVA or the analysis of variance tests. Tests with more than 2 groups are assessing whether there is some difference between the groups, but it doesn't tell us which group is different from the others. If we have a test with 4 groups, we can run it on an ANOVA, and it will give us, say, a p-value less than 0.05, which means that there's a statistical difference somewhere in there, but it doesn't tell us which group is different. We would then need to do further testing, 2 groups at a time, to determine finally which group is the one that is significantly different. And this further testing after an ANOVA or after the initial analysis is called post hoc testing. We won't get into that in this course, but it's good to know that that's the process. Finally, we're asking ourselves, what kind of variable are we assessing? So statistical variables each have a different type of underlying statistical distribution, and therefore each requires a different statistical test. There's a different test for nominal, ordinal, and continuous variables. This figure is simply showing that there are different types of underlying distributions and kind of why we would need different tests. So to recap the variables from last week, there was nominal, ordinal, interval, and ratio data. Nominal and ordinal data are both discrete variables. Nominal data is essentially categorical, in which we can't rank these discrete options. We can only essentially do frequencies. Ordinal data is where there's a distinct rank order to the discrete variables, like pain scores. And then there's continuous data, which we'll treat essentially similarly this week because the tests we use are the same. For continuous variables in particular, we also need to ask whether the distribution is parametric or not, whether it's normally distributed or shaped like a bell. Many tests for continuous variables, notably the t-tests and some other tests, have certain requirements that must be met in order to use the test in practice. And these include that they must have independent variables, use continuous data, have equal variances, but also that the variable must be normally distributed. And remember, a normal distribution looks like this figure here, in which the data is normally distributed around a central mean, and the mean, median, and mode all take the same value. So continuous data must be parametric to use t-tests. For the next slide, we'll look at continuous data. If it's non-parametric, then we'll look at how we should be using ordinal tests instead. If I wanted to use a t-test but my data wasn't parametric, I would then switch over to using the ordinal test for two group independent variables. All of this statistical discussion kind of accumulates into this final slide of video 1, choosing the correct statistical test. I'll provide this table to you on your quiz, but be prepared to be able to assess independence or dependence, number of groups, and type of variables in order to use this table most correctly. So this table is broken up into, first of all, based on independence or dependence. If we're looking at tests for two dependent groups, in other words, the same patients were used to generate both sets of data, kind of like the before and after data, then we would use these first three columns. For nominal dependent data, we would use the McNamara test. For ordinal dependent data, we could use the Wilcoxon-Sign rank test. And then for dependent continuous data, we would use the paired t-test. A t-test, but essentially paired variables. So if I was measuring a diabetic patient, I could look at their blood glucose before and after the pharmacist had talked to them, and I could do that for the whole large group of patients. That would be dependent variable, but continuous. Blood glucose is a continuous ratio variable. I would use the paired t-test because there's two groups as well. The next three columns in this flow chart are for two independent groups. So two groups which are different patients. If I was using nominal variables, I would use a chi-square test if I had two independent groups. If I was assessing pain scores or an ordinal variable, I would use the Wilcoxon-Mann-Whitney test. And if I was measuring a continuous variable, I would use the t-test. If we're looking at more than two independent groups, so three or more independent groups, again, the nominal test is still the chi-square test. You can use that on three or more groups, but the ordinal test is the Kruskal-Wallis test, and the continuous variable test is the ANOVA. Now remember what we just said on the last slide. If the continuous variable is non-parametric, so if I have two independent groups with a continuous variable, I'm trying to use the t-test, but my data is non-parametric. I would then switch over to the ordinal test, which is the Wilcoxon-Mann-Whitney test. So know how to use this table and arrive at the correct test for your quiz in the coming week.